Good morning, afternoon, or evening, based on where you are connected. I am Davide Ghiglino. I am a PhD student working at the Istituto Italiano di Tecnologia, jointly with the University of Genoa. Today, I will present you the results of one of our studies that investigated the sensitivity of a group of participants to subtle hints of human likeness that was displayed by our ICAB robot, the humanoid that is cheering you into the slide. So the main reason why we are interested in answering such experimental question is related to the fact that artificial agents are entering our lives at a certain speed. Besides, little is known about social cognitive mechanisms that are evoked during the interaction with artificial entities. Already in the 80s, a philosopher, Daniel Dennett, postulated the existence of different stances, different attitudes that we adopt when we interact with different kind of agents. He hypothesized the existence of an intentional stance that we adopt toward agent whose behavior can be explained and predicted with reference to their intentions, beliefs, emotions, and more in general, mental states. And if we think about our everyday life, the adoption of this stance is pretty common. We rely on it every time we interact with our conspecifics, with our friends, with our families, and so forth. However, when we interact with other kind of entities, artificial entities such as our computers or with our smartphones, we do not need to rely on such complex mental representations. Their behavior, the behavior of artificial agent, can usually be explained with reference to their functioning and to the way they are designed to work. This attitude is what Dennett calls the design stance. Indeed, the adoption of the design stance or the intentional stance does depend upon several factors, ranging from the characteristics of the agent, the behavior it displays, but also on the knowledge that the subject has about the agent, contextual cues, and additional beliefs and emotional states. What we are interested is to understand whether we can evoke the adoption of the intentional stance by manipulating the behavior of an artificial agent, by taking advantage of the natural tendency of humans to anthropomorphize entities for which they lack a specific knowledge, in our case, humanoid robots. For these reasons, in our studies, we investigate the behavioral parameters that are able to elicit in the human the adoption of a mentalistic vocabulary to explain and predict the behavior of a humanoid robot. Additionally, we are interested in assessing individual differences that can modulate human sensitivity to such behavioral manipulations. Our approach is fairly straightforward in the sense that we start from the observation and the recording of a human behavior. We copy it as it was recorded into the robot, and we create situations of interaction. In this specific case, you will see just observation, not a real interaction. Observation or interaction in which participants are exposed to the behavior we implemented into the robot. Actually, between step 2 and step 3, we usually generate several behaviors based on the human recordings. Some of them can be defined human-like, in the sense that are exact copy of the behavior we recorded from the human. And here you can imagine the level of variability we face in the process of implementation, while some others may be defined machine-like, as we only take an average behavior from the recordings and we reproduce it repetitively, eliminating all the variability from the movement and its kinematics. So in the present study, we recorded a set of participants while they were playing a solitaire card game on a laptop in front of them for approximately 8 minutes. During the play session, from time to time, we try to distract them using video acoustic stimuli that were presented on a lateral screen. Basically, we used an attentional capture setup to collect human recordings. For the sake of brevity, here I won't present you with the entire process, but only with the final product. So here in the first video, sorry for the background noise, you can see what we call a human-like behavior. You can see saccades and in general the reproduction of our recordings. The robot is basically reproducing for 8 minutes the entire stream of data we collected from one of our participants. Here you see the robot reacting to a stimulus, but in general, implementing a human behavior into the robot means that the robot is sometimes turning toward the screen, sometimes ignoring the distracting stimuli, sometimes it is focused on playing, and so forth. So the variability is huge and displayed not only through the movement of the eyes, but also through the movement of the head. Here you can see the second behavior that we designed, machine-like behavior. The robot is behaving in a very repetitive way based on the average of the recording, meaning that from the point of view of the eye movement, it scans in exactly the same way for the entire duration of the behavior, the screen in front of it, and it turns with exactly the same repetitive movement every time a sound is presented on a lateral monitor. We asked 79 participants to observe the two behaviors. The order of presentation was counterbalanced. And after each behavior, we asked them to fill the instance test and the Godspeed questionnaire that I will present you in a moment. At the end of the entire experiment, before the briefing participant, we asked them whether they noticed any difference between the two behaviors. And if the answer was positive, we asked them which one was more human-like according to them. We divided our participants into two groups and we manipulated their prior knowledge of the experiment. We provided full instruction to one group, informing them that one of the two behavior would be a copy of a human behavior, while the other would be a behavior generated by the experimenter ad hoc for the experiment, and that their task would be to identify the human-like behavior. To the other group, we provided no instruction. We simply asked them to observe the behavior and that all information related to the experiment would be revealed after the debriefing. Here you can see some examples of items of the two questionnaires I mentioned above, the instance test and the Godspeed questionnaire. The instance test is a test that we developed a couple of years ago, and it's aimed at assessing whether individuals tend to explain the behavior of the ICAB robot using a mentalistic or a mechanistic vocabulary. It can provide a loose indicator of participants' tendency to adopt the design or the intentional stance toward the humanoid. The Godspeed questionnaire is a commonly used questionnaire in social robotics that evaluates how individuals perceive a robot based on the attribution of human-like characteristics towards it. We used only few subscales of the questionnaire, the ones that are assessing anthropomorphism, animacy, and likability perceived by participants. So now that you have an idea of our dependent variables, I can present you the main results. The scores of each questionnaire were our dependent variable, and we included them in a series of mixed effect models. For each model, we included the subject slopes as a random effect, while the instructions, explicit versus no instruction, and the behavior displayed by the robot, human-like versus machine-like, were included in the models as fixed effects. Our results pointed out an interaction effect on the anthropomorphism score between instruction manipulation and behavior displayed by the robot, supported by a main effect of the behavior. Specifically, participants tended to attribute higher anthropomorphism to the human-like behavior than to the machine-like behavior. And this effect is significantly evident when the instructions provided are explicit. Exactly the same pattern, meaning the interaction and main effect of the behavior, was found on the animacy scores. These results suggest that the attribution of anthropomorphic characteristic might depend mainly on individuals' expectation and knowledge than on perceptual cue per se. Besides, we found the main effect of the instructions on likability, indicating that the participant liked the robot more when they were unaware of the experimental manipulation. In order to further explore our result, we took into consideration the explicit attribution provided by the participants at the end of the experiment, corresponding to their ability to find the differences between the behaviors and to their attribution of human likeness toward either the human-based behavior or to the machine-like behavior. As you can see, and this is already an interesting qualitative result, I think, almost half of the sample that received no instruction was unable to spot any difference between the two conditions. Curiously, 1/4 of both samples made a wrong attribution. We decided, therefore, to apply another set of models, including these participants' explicit attributions, as a fixed factor, along with the behavior of the robot. We analyzed separately the two groups of participants. In the group that received no instruction, we found an interaction effect between explicit attribution and robot's behavior, indicating that participants misattributing human likeness tended to like more the robot displaying the machine-like behavior, thus confirming their bias. In the group that received explicit instructions, we found a systematic interaction between the explicit attribution and the robot behavior on all the scales of the Godspeed, indicating that participants making the correct human likeness attribution perceived the human-based behavior as more anthropomorphic, animated, and likable. At the same time, participants providing the unexpected attribution displayed the reverse pattern, rating higher the anthropomorphism and the animacy of the machine-like behavior. So to summarize our result, when we prompted our participants' attention to notice hints of human likeness in the behaviors of the robot, they tended to differentiate more their answers in the Godspeed questionnaire between conditions. As if their perception of anthropomorphism, animacy, and likability depended mainly upon their belief of what a human-like movement should look like. This suggests that subtle evidences of behavioral evidence of human likeness might be too weak of a signal during tasks that merely involve the observation of artificial agents' behavior. And this might be related to the fact that in natural interaction with humans, we are usually not monitoring, or at least not being asked to monitor, the human likeness of the counterpart's behavior. Thus, human likeness might be an implicit feature of human behavior, which we derive only if needed to explain the behavior of a non-human agent. Therefore, during everyday life, our sensitivity to such subtle hints might be extremely low, as we might perceive it is more likely, at least, a gestalt relation between behavioral and contextual elements, rather than pure and distinct behavioral features. Taken together, our results suggest that the differences in knowledge between participants override perceptual evidence and sort of tweak individual sensitivity to behavioral cues. In conclusion, our study suggested that individual knowledge, beliefs, and biases play a major role in modulating human perception of an artificial agent behavior. And these influences seems to be even stronger than perceptual evidences during observational scenarios and need to be taken into consideration for future study. So with this, I thank you very much for your attention, and I think I can open the floor to discussions and questions. Thank you again.